This is David Kasmer, a professor of plastics engineering at the University of Massachusetts Lowell and the inventor of injection printing. Injection printing is an additive manufacturing technology that combines the flexibility of 3D printing with the strength and speed of injection molding. Injection printing uses 3D printing to provide the inner and outer shells of the component geometry, along with any desired feature details or internal geometry. We then use the nozzle of the 3D printer as an injection unit, filling the internal cavities by using the 3D printed shell as its own mold. The physics allow cavities that are several layers deep and wide, thereby increasing the production speed, heat transfer, and bond strength. For example, if the roads that make up the shell walls are 0.5 millimeters wide, 0.2 millimeters high, and printed at a speed of 40 millimeters per second, then the volumetric flow rate during printing is 4 cubic millimeters per second. By comparison, the filling of the internal cavities formed by the shell walls is far more than that, allowing reductions in print times by a factor of 3 or more. Here are some images of tested specimens. Note the large fracture surfaces as well as crazing at multiple occasions along the length of the tested specimen. These provide evidence of the improved bond strength and validated part properties. There are two main reasons for the increased part strength. First, the parts are much more dense than typical 3D printing, since the injected melt tends to fully fill the cavities between the shell walls. Second, the injected melt provides much more thermal mass than a typical road, allowing the weld interfaces between the injected material and the surrounding shells to fully heal. What is really cool is that injection printing is backwards compatible with any 3D printer. Here I'm using a stock Keedy X Pro with its stock nozzle and stock firmware. I just provided the G-code to do the injection printing. So injection printing provides an average increase in print speeds by a factor of 3, along with significant improvements in mechanical properties. The limiting factor is just the melting capacity of conventional 3D printers. With some simple upgrades, the print speeds are increased by a factor of 5 or more, while enabling more flexible printing strategies that increase the print resolution and product properties. If you're interested in more details, please see our article on injection printing published online in July of 2020 in the Journal of Additive Manufacturing, or contact us at the University of Massachusetts Lowell Department of Plastics Engineering.